Welcome to another video explaining the universe using the particle model. Well, today's video is the last video on the senses, and this is about sensing the temperature. And I've been using the Howard Hughes Medical Institute series on senses and sensitivity, sight and sound, and I've added to that olfactory, sensories, and today temperature sensing. Typically this would have been the fourth video going through this explaining and making the sense of sensory information. But the fourth video in the series explores how the sight and sound are mapped on the brain. It's interesting, but it does not relate to the particle model in a way that helps explain the mapping. So I'm giving you my own interpretation of how we sense heat and what our body does about it. So let's talk about heat for a minute. In thermodynamics, heat is energy transferred to or from a thermodynamic system by mechanisms other than thermodynamic work or transfer of matter. The mechanisms include, and these are kind of traditional, conduction through direct contact of immobile bodies or through a wall or barrier that is impermeable to matter, or radiation between separate bodies, or isochoric mechanical work done by the surroundings on a system of interest, or joule heating by an electric current driven through a system of interest by an external system, or a combination. Well, if you go back to elementary school, they really talk about three different ways of heat transfer. Radiation, which actually generates electromagnetic waves or light waves. Conduction, that's when two objects touch and the heat is exchanged. And then there's convection, that is, warm objects heat the gas or fluids, and the fluids then in turn move and heat other objects. Convection. Now here's the first one I'm going to cover. It's the radiation. Interesting picture of a human body emitting that, and the EM radiation, to skip down here at the bottom, has wavelengths from 0.7 micrometers to 1 millimeters. Long wavelength, shorter wavelength, but they're all above visible. You can't see this by your eye, and yet here we have a picture that shows in color and a graph that relates that color to the temperature. And so they must take, when they take these pictures, they have to downshift the high frequency short wavelength to lower frequency visible light and a wider wavelength. And so these colors are not really, they're just there to help show the thing. And you can see that we're radiating light at higher temperatures. Here their skin is more exposed. Here they're wearing clothes, and you still get it through that. And you have all three here. You have direct radiation out of the body, but you also have your hand heating the air. That's convection. And the body also heats the clothes, and that's conduction. So you have all three of them in this one picture. Okay, heat, for the most part, is sensed at the skin. Part of what I read about temperature sensing is that there's heat sensors all over our body, everywhere. And in your mouth, in your eye, in the bladder. Those were three specific examples that I saw, and I'm not going to go into that so much. But this is in the skin, and you have all these sensors. Oddly enough, the first one listed here on the left is the thermoreceptor, which senses heat and cold. And normally this is shown much closer up here to these to the skin. Here's a sensor for touch, and there's a sensor for sensing pain. And these are different sensors, and they briefly talk about those, and I'm not sure the way they're described how different they are, but pain is certainly different when you get a pinprick. And then there's the senses of pressure in the skin. We're only going to talk about this one, but all these sensors are in the skin, and there's so many more sensors throughout our body. So the sensors for heat are called thermoreceptors, and there are many types, as I just said. There's in the eye. When your eye gets too warm, you have tearing. In the mouth, apparently there's a condition where, for example, where food tastes differently when it's cold versus when it's hot, and there's an effect of our taste buds when the food is cold. And then there's the bladder. They never explained that. Maybe it has to do with infection. I'm not sure. But here are typically these sensors, as I mentioned before. This is the edge of the skin, and this is very close to this layer. And they have cold receptors and warm receptors. Well, in terms of the particle model, this would be my understanding of sensing heat and cold. Our body uses the vibrating atoms, molecules of the skin to release G1 particles to the brain. In other words, as these molecules in the sensors in the warm receptor, they get more active. They're more likely to interact back and forth, hitting each other, releasing more. Cold receptors, this is different. So the outside temperature, if it's hot, causes our atoms molecule to go faster. If the outside temperature is cold, it causes them to move slower. That's my perception of what could be happening. But let's see what the text says from the internet. Warm receptors will turn up their signal rate when they feel warmth. They talk about signal rate. And whether it's amplitude or rate, it doesn't matter. Higher vibrating atoms are going to generate it faster and maybe stronger, both. And that's when they do that, when they feel warmth or the heat transfer into the body, causing the molecules to, or the heat transfer out of the body results in a decreased signal rate. Now, so the warm receptors, and this is the cooling, and this is the same receptor, the way I read this from the text, and this makes a lot of sense to me, that maybe on the average, while your body is at its normal temperature, it sends a rate, and then it turns up the signal rate when it gets warm. It slows it down. Makes perfect sense to me. But then they bring in the cold receptors. They call the warm receptors does this, like it does both. Cold receptors, on the other hand, increase the fire rate during cooling, and it increases the firing rate during cooling and decreases it during warming. According to what I just described, this doesn't make sense. Personal story. Yesterday, I went to the dermatologist, and I'm looking at the wall while I'm waiting for the doctor to come in, and they have the picture of the skin right there, and it immediately reminded me of this. And so I'm asking the nurse, poor nurse. I'm asking her this question about warm receptors and cold receptors and how this part of the explanation doesn't make sense. Ironically, as I left the office, actually as she left and I was getting ready to leave myself, she said, if she finds the answer, she's going to call me. So maybe I'll get an answer. Okay, moving on. Okay, our body's response to losing heat. I hope I did this right. No, I skipped one. All right. Here was a different answer. I found this in scientific, in this link. They talk about low threshold and high threshold receptors. But this one references pain. And the low threshold receptors are activated by temperatures between 15 and 45 degrees C, which are not usually painful. This is kind of the normal range. And the brief stimulus during is usually used for assessment. They do not cause damage. If they're not painful, the pain is there to tell you there's damage. So there's no damage to tissue, and this is sort of just normal operation, low threshold. High threshold receptors respond mainly to temperatures higher than 45 and lower than 15. Are these two separate receptors? Couldn't find out. I looked around, read several articles. This is another one that it doesn't make sense that this is one type of threshold detector that can do cold and hot, very cold and very hot, and typically probably are painful. So that's a different answer. And this one works very much with, like the particle model would say, at the low temperatures, there's a low rate of signaling. At a high temperature, there's a high rate of signaling. Okay, our body's response to losing heat. If the air is cold, the air molecules vibrate less, and our atoms will cause the air to vibrate more, and the air will cause our atoms to vibrate less. I ran through that real quickly. The thing is, if the air is cold, air molecules are vibrating less. Our atoms will cause the air to vibrate more. In other words, for every action, there's kind of an equal and opposite reaction. If it were a closed ideal system, you could say that. In a normal environment, things are not ideal, but there is actions both ways. Kind of my understanding that heat transfers in one direction but not the other. No, I'm saying here that the warm body cools down, warms up the air while the air cools the body. And the air will cause our atoms to vibrate less. That's why we get colder. We feel cooler, that is, we feel the loss of heat. When we lose too much heat, our body senses that and causes us to shiver and get goose bumps. Well, why does it do that? It does it automatically. We don't ask it to do that. Shivering is one such tactic in which we control the temperature, in which your muscles contract and expand in speedy spurts. That's the way muscles work, by the way. It's really a contracting signal. When it's a strong signal from the brain to the muscle contracts. When a weaker signal or no signal is sent to that muscle, it relaxes and expands. In addition to quaky limbs, your jaw muscles might begin to shiver, making your teeth chatter. This twitching exercise produces heat, which helps raise the body temperature. What does it do? The twitching in your muscles causes your atoms to vibrate. It is mechanically forcing your atoms and molecules to vibrate so that the temperature is increased in those areas, protecting the organ that it's protecting, in this case the skin. But you also get goosebumps. Goosebumps appear due to piloerection. This is one of the reactions that occur when the temperature is too low. This again, we're talking about cold, losing heat. This causes hair to stand on end as a result of contraction in the muscles. Again, the muscles around the hair follicle, muscles attached to the hair follicle called erector pili. Hence you get the reverse term here, pileo-erection. And when the brain sends a signal to a strong signal to this muscle, it causes the hair to stand up straight. And when it sends a weaker or no signal, that muscle relaxes and the hair lays down. This particular reflex is not actually important in human beings. However, in animals, this mechanism allows an entrapment of layer of air, allowing insulation. This way, the heat loss is greatly reduced. So their hair around their body expands, trapping air. Their body heats the air, giving an insulation layer. Interestingly, though, fear also causes goosebumps. Animals use this as a defense mechanism, making themselves look larger, more fierce when they try to defend themselves. Okay, a response to gaining heat that we discovered losing. Secretion of sweat occurs when the myoepithelial, boy, that's a word I don't say very well. These cells surrounding the secretion glands, they contract. Again, the brain sends signals to the cells. This is a picture of the cell under normal condition. There may be a small amount of perspiration there even under normal. What happens when you gain too much heat and it wants to cool the body, it sends a signal, strong signal to this muscle, contracting this, pushing more out, and eventually it can push so much out it vaporizes. Eccrine sweat increases the rate of bacterial growth and volatilizes, or at least causes this process. The odor compounds of apocrine sweat, strengthening the layer's acrid smell. There's a combination of the apocrine sweat, which is normal. Apocrine sweat causes this bad smell that we get. Not sure why we have to have a bad smell when we sweat. Maybe that's a repulsive odor for our natural enemies to go away. Well, this is kind of a conclusion of all my videos on the senses. And the particle model, to me, has a reasonable explanation for the olfactory senses, the oral senses, and the visual senses, but not necessarily for the temperature sensing. As I indicated in this video, there are parts that I couldn't get enough information to explain how it works. In one case, higher vibrating atoms release more G1 particles into the neuron. That makes sense. Slower moving ones release less, and if the brain has a threshold over which it monitors, it can tell you whether you're gaining or losing heat by whether that's increasing or decreasing or being stable. Well, yeah, maybe I don't have the temperature sensing right. I'm not a biology expert, and I don't have enough information on this to understand how they work. But it's kind of interesting to apply the particle model to biology, and maybe it could be applied to plants as well. I have a friend named Artie Rantham who has studied the effect of magnetic fields on plants. That's not the same thing as, but an electromagnetic field is part of what I discuss. And if I get a chance in the future to talk to Artie, I may ask for him to help me do something along the line of plants. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I explain more of the universe using the particle model. Thank you for your attention.